You ever just stop and think about how wild it is that our eyes can take in this whole huge world and just create a perfectly sharp picture? It's amazing. In this explainer, we're going to pull back the curtain and look at the basic optical principles that make it all happen.
So, how do we get from scattered rays of light flying all over the place to a crystal clear image? To figure that out, we're going to follow a single ray of light on its incredible journey. We'll track it from the moment it hits the very front of your eye to the instant it lands perfectly focused on your retina. You'll see it's all about some really elegant physics. Okay, so our journey begins right at the surface of the eye. And the very first thing that happens is a process called refraction. This is, without a doubt, the most important first step in creating vision. So what is refraction? Simply put, it's just the bending of light. When light goes from traveling through the air to traveling through the, watery stuff of your eye, its path literally bends. You've seen this a million times. Think of a straw in a glass of water. It looks bent, right? That's refraction. And that same effect is the absolute key to focusing an image. Now, this bending isn't random, not at all. It's actually governed by a super precise rule called Snell's law. You don't need to memorize the formula, but what it tells us is that we can predict exactly how much that light is going to bend. It all depends on what it's traveling through, say from air into the cornea. And that predictability, that's the secret sauce for everything else we're going to talk about. See, the eye isn't just one single lens. It's actually a whole series of surfaces, and each one bends the light a little bit more, according to Snell's law. So light hits the tear film first, then the cornea, and the cornea does most of the heavy lifting here. Then it goes through the aqueous, the lens, and finally the vitreous. Each little bend refines the focus just a little bit more. And this is why understanding refraction is so critical in the real world. When that bending goes wrong, you get vision problems. In a condition like keratoconus, the cornea's shape is irregular, which messes up the bending and distorts the image. So what do? Well, a contact lens just puts a new, perfectly shaped surface on top. And something like LASIK surgery actually reshapes the cornea itself. See, it all comes back to controlling that bend. All right, so light has entered the eye and it's been bent. But now what? How does the eye take all those different bent rays and pull them all together to form one sharp image? For that, we need to introduce a new concept called vergence. So, vergence. It sounds technical, but the idea is pretty simple. It's just a way to measure whether light rays are coming together or spreading apart. Vergence basically puts a number on the direction and power of those light rays. And really, it breaks down into two camps. Light rays are either converging, that means they're coming together towards a point, and we call that positive vergence, or they're diverging, spreading out from a point, and that's negative vergence. This simple little distinction is actually the key to understanding why some of us need glasses. And here's where it all clicks. Common vision problems are really just vergence problems. If you're myopic or nearsighted, your eye has too much converging power. It's too strong. It focuses the light in front of the retina. If you're hyperopic or farsighted, your eye has too little converging power. It's too weak, and the focus point falls somewhere behind the retina. Okay, so now we know the problem is either too much or too little vergence. So how do we fix it? Well, we use the perfect tools for the job, lenses. The power of a lens, which we also measure in diopters, is just a way of saying how good it is at changing the vergence of light. A really powerful lens bends light a ton, while a weaker lens just gives it a little nudge. So, just how powerful is the human eye? Well, get this. The cornea by itself has about 43 diopters of focusing power. 43. To put that into perspective, a really strong pair of reading glasses might be 3 diopters. The cornea is an absolute powerhouse. It's doing almost all of the focusing work. And right behind the cornea, you have the eye's internal lens. It adds another 17 diopters or so. But this lens has a superpower. It can change its shape. And that process, which is called accommodation, is what lets you instantly shift your focus from something way out in the distance to the words right here on your screen. It's like the eye's own built-in autofocus system. It's pretty incredible. So it becomes a simple toolkit, right? For farsightedness, where the eye is too weak, we use a convex or plus lens to add a little more converging power. For nearsightedness, where the eye is too strong, we use a concave or minus lens to add some diverging power to cancel it out. It's a perfect balancing act. And I want to be clear, this isn't just theory. These principles are used every single day in clinics and operating rooms. From writing a simple glasses prescription to calculating the exact power of an artificial lens for cataract surgery, it all comes back to these core ideas of power and vergence. So let's put it all together. We've looked at the different pieces of the puzzle, but now let's see how they work together as one single unified system. Let's recap that whole journey of light.
And there you have it. It starts with refraction, that initial bend of light. That creates vergence, causing the rays to converge. And when that convergence isn't quite right, we use lenses to manipulate it. It's all one beautifully interconnected system, with three principles all working together for one goal, giving you a perfectly sharp image of the world. So these rules, refraction, vergence, power, they are the bedrock of modern vision science. They're why we can fix vision with glasses, contacts, and surgery. But you have to wonder, right? Now that we've got these rules down, what's next? What new technologies are coming that will build on this foundation and enhance our vision in ways we can't even imagine yet? That's the exciting part.